At the most basic level, there are 4 fundamental forces in the universe. So all the forces that we've talked about up to this point are really manifestations of these 4 forces. The first is gravity. You all understand gravity. You've heard the term gravity. The pull from objects with masses. We've talked about that in class. Then, of course, there's the electromagnetic force, which we talked about earlier this semester. The pushes and pulls of charged particles on one another and magnetic forces from other magnetized objects. There are 2 forces that act on the atomic nucleus itself. There's the weak force and the strong force. Named as such because one is stronger than the other. So these 4 forces comprise the main forces in the universe. Looking at their relative strength, how strong are these forces with respect to one another? Well, if we consider the strong force to have a force of 1, right, the most powerful force of the 4, how do the others stack up? Well, the weak force is more than 10 trillion times weaker than the strong force. The electromagnetic force is 100 times weaker. And gravity is almost 40 orders of magnitude weaker. 10 to the minus 38. That's a 0.000 with 37 zeros and a 1. So gravity is by far the weakest of these forces. So why is gravity the one we're most intimately familiar with, right? The fact that you walk up a flight of stairs to get to your classes and you're winded at the top, or you walk up Rib Mountain and you're tired from the ascent, you're fighting gravity on the way up. Why, being so incredibly weak, is gravity the most obvious force in our everyday lives? And the answer is gravity acts over an infinite range, and it is an attractive force only, meaning masses pull and attract one another. There is no anti-gravity. There is no repulsive force. All the other forces are both attractive and repulsive, and those equal and opposite forces can balance out. So all the protons on the moon are pulling on your electrons in your body, but all the electrons on the moon are pushing, and those forces balance out, and you feel no electromagnetic force from the charged particles on the moon because of the cancellation of the positive and negative forces. Gravity is only positive. There is no cancellation, therefore, even though gravity is incredibly weak, there's a lot of mass in the Earth, and therefore you feel the gravitational pull of that mass. Electromagnetic forces also acts over infinite range, whereas the weak and strong force have incredibly limited ranges. The nuclear weak force, less than 10 to the minus 18 meters. To give you a sense of scale, an atomic nucleus is 10 to the minus 15. So this is 1,000 times smaller than the nucleus of an atom. The strong force is around the size of the nucleus of an atom. Now, we talked in the previous video about carrier particles. For the strong force, we said pions were the carrier particle, but pions are actually thought to be made up of, smaller particles called gluons. Now, we've detected pions in particle accelerators. However, we have not yet observed gluons. So these are theoretical or conjectured particles. For the electromagnetic force, photons. Well, we've seen photons. There are virtual photons that exist between particles. When 2 protons come together, they exchange virtual photons and then push each other apart. However, photons also exist not just as virtual particles, but in the real world as well. That's how you can see me on the monitor where you're watching this show. Photons are being emitted from the monitor, go into your eyes, and are being detected by the retina. For gravity, physicists think there is a particle called the graviton. That's the carrier particle. That's the particle that's being exchanged between you and the Earth, telling the Earth that you're here. And the Earth is telling you that it is there. Those are also not observed. So if gravitons are detected, right, that would be a wonderful bit of supporting evidence for this theory. or if gluons are finally detected in the future, that would be a wonderful bit of supporting evidence for this theory. However, if they're not detected, eventually this theory might go by the wayside and something different might come about. For the nuclear weak force, we have W plus, W minus, and Z neutral, basically, particles. These are, again, exotic particles that exist over ridiculously short lives because they're massive particles. Massive particles can only have short lives before the universe questions where the energy came from. So they exist over very small periods of time. Very small period of time, so they can't travel far before they disappear. Whereas the graviton and the photon is a massless particle. So virtual photons can go over infinite ranges. Gravitons would also have to be then a massless particle. The more mass a carrier particle has, the shorter life it has, therefore the shorter distance it can affect other particles before disappearing. Now, how does this exchange of carrier particles work? Well, there's a diagram here your book talks about from Feynman. Richard Feynman was a famous American physicist, worked on the Manhattan Project, which you talked about a few videos ago. And he came up with the idea of what's called the Feynman diagram. It talks about how two particles interact with one another via a messenger particle. And these diagrams are very, very popular in quantum mechanics. If you take advanced physics courses, you see these quite a bit. At the most fundamental subatomic level, right, electromagnetic forces, we dealt with labs dealing with electromagnetic forces. We did labs, or we don't have to do labs dealing with gravity. We did last semester when we had free fall labs. But these work over infinite ranges, so they work on scales that we are comfortable with, that we can see in the everyday world. The nuclear weak force and strong force only work at subatomic scales. We can't do an experiment in class to show you the nuclear weak force in the everyday world, or the nuclear strong force in the everyday world. The forces act over too small a range. Even though the electromagnetic force and gravity work over infinite ranges, physicists have difficulty trying to explain how these forces work at the subatomic level, specifically gravity. But there is a field of study called quantum electrodynamics, or QED, quantum electrodynamics, which is the quantum mechanical field dealing with electrodynamics, dealing with the motion of charged particles. It describes the electrodynamic interactions between particles on the subatomic scale. So rather than electromagnetic forces talking about how we get wire through, or electricity through a wire, or why you can rub a balloon in your hair and stick it on a wall. Those are macroscopic applications of electromagnetic forces. Quantum electrodynamics talks about how an electron actually affects another electron. And again, using these Feynman diagrams to talk about how carrier particles, these virtual particles, can talk, basically are exchanged between these particles, and therefore a force is applied between these particles. So this covers basically the four basic forces, and we're going to talk shortly about the basic particles in the universe.